So, welcome student to the next class of Introduction to Nonlinear Optics and its application. So, in the previous class we have learned the light propagation in the anisotropic system. So, we will continue that because it is a very important thing that you need to learn in the context of nonlinear optics, because we find that it will going to help us to understand how different kind of phase matching will appear in this kind of crystal where anisotropy is one of the fundamental nature, and by using this fundamental nature how we can use the phase matching. So, that is why the learning of this anisotropic system is very important. So, let us go back to our topic today. So, today we will going to learn as usual electromagnetic wave propagation in anisotropic medium. This is a subject, this is a topic that we are covering for last couple of classes or more than that. Then ordinary extraordinary wave or ordinary extraordinary ray, that also we have discussed in the last class. Then index surface we have discussed. So, today we will going to understand what is index ellipsoid and try to calculate how one can generate this index ellipsoid, and finally, the linear response and polarization. So, it is very important the polarization, because the nonlinearity will be appearing if we will have a polarization where the response of the system is nonlinear. So, we will learn that in detail. So, go back to our slides. So, this is the old slides I am using. These slides we have already used in our last class, that how the refractive index n is a function of theta. Here we can see that in this case, that this is a theta or angle phi, whatever. What is angle phi? The angle phi is a launching angle. So, k vector is here. So, k vector is making an angle phi with respect to an axis, z axis, and we mentioned that z axis is the axis along which the wave is propagating, and if in this direction the wave is propagating, then what happened, that the refractive index for ordinary and extraordinary ray will be same. So, now if I launch any arbitrary direction, the k vector in any arbitrary direction, for example, here in this figure, then what happened, that there is a difference between the refractive index. You can see there are two circles are drawn here, we call these circles at index surface. So, these two circles basically represent the amount of the value of the refractive index in particular direction. So, in this 2D representation, if I launch the k vector along whatever the direction, so 360 degree direction one can have. So, in that case what happened, that the refractive index value here will be a function of phi, and how it will be related to NO and NE, where NO and NE is a refractive index along x direction and y direction, x direction and z direction in this case. So, along z direction we call the refractive index NO, and along x direction we call this refractive index NE. So, that means NO and NE are not same. So, I should write here one important equation, that NE is not equal to NO. That is why what happened, that this shape become ellipsoid, so or ellipse in this case. So, that means by changing the launching angle we can have different refractive index, and one can have the value of refractive index if n0 and NE is given to him or her. Then by using the value of phi, that means at which angle I am launching, in this case here this is the angle, I can able to find out what is my n phi just using this expression. So, n is also related to our previously defined parameter k, big K, we have already defined that. So, it is nothing but root over of k x, k y and k z. For uniaxial crystal, the refractive index along x and y is same, and it is k x and k y both are same, we call it NO, and Kz is different. So, we call it Ne. So, these things we have learned in our previous class. So, I am not going to take much time on discussing this. So, go back to our next slide. So, now it is positive crystal and negative crystal. In the last slide, I mentioned an important thing, that NO is not equal to Ne. That means, refractive index of ordinary wave is not equal to the refractive index of the extraordinary wave, and the extraordinary wave and ordinary wave, they are propagating at different velocities, obviously because their refractive index is different. So, based on that information, I can find out two different kind of system. One is positive crystal and another is negative crystal. So, in positive crystal, if you see here that ordinary velocity of ordinary wave is greater than velocity of extraordinary wave. That means, refractive index in terms of what is velocity here inside the medium? We know that it is nothing but c divided by n. This is the velocity. So, once I say this is VO or the velocity of the ordinary wave, then obviously I should write VO is equal to c divided by NO. In the similar way, I should write VE is equal to c divided by NE. So, now if the velocity of the ordinary wave inside the medium is greater than velocity of the extraordinary wave as shown in here, then the crystal is the positive crystal. So, now if I write this equation VE VO in terms of any NO, so let me do that. So, I say VO here is greater than VE. So, in another word, if I write in terms of refractive indexes, so c divided by N0 is greater than c divided by Ne, c cancel out. So, Ne should be greater than No. So, that means in the positive crystal what happened, the refractive index of the extraordinary wave is greater than the ordinary wave No. So, this is the figure of positive crystal. So, let me remove this part. So, this is the figure of this positive crystal. So, you can see here that this green line or the green ellipse corresponds to the refractive index difference or the refractive index variation with respect to the angle phi. So, that means this is the extraordinary refractive index which has an angle phi. When the phi is pi by 2, we know that this has a maximum value and this value we designate as Ne. So, here in this point. So, Ne is this amount, this is the amount from here to here, from this value to this value, this is my Ne. What is NO? NO is a constant value because this is a circle. The radius of the circle here is constant. So, obviously, whatever the value you can choose as a radius will be the value of NO. So, NO is the value of this radius of this red circle and this amount is Ne. You can see that the value of Ne gradually change when we change the angle phi. Obviously, that should be because that is the equation we had in our last class. So, when the angle of the phi is 0, then NO and Ne will coincide, that means at this point. If I again write this equation, so 1 divided by Ne I should write is the extraordinary wave, this is a function of phi is equal to so let me write once again the equation 1 divided by n square phi E is equal to cos a square phi divided by NO square. This is the same equation that was shown, sin square phi divided by NE square. So, when phi is equal to 0, then NE square is nothing but NO square. That means, the value of NE is coinciding with the value of NO. That means, this is the point I am talking about. On the other hand, when the value of phi is 90 degree, pi by 2, then the value of this quantity will be equal to value of this. So, that means, that is the value of the refractive index along z direction, and there is a difference between this and this, and also another thing is that NE here greater than NO. So, that is why this kind of crystal is called the positive crystal, and this is typically the figure of the index surface for positive crystal. Well, if there is a positive crystal, then the next question is whether there is a possibility to have a negative crystal. Obviously, there is a possibility to have the negative crystal, because here we find that the velocity VO is greater than VE, but here we will find that the velocity of ordinary wave is less than the velocity of extraordinary wave. So, here my condition is VO, just the opposite, is less than E, and in terms of refractive index I can say that NE is now less than NO. If that is the case, then the modification here we have is we have a circle as usual, and the ellipse that will be the value of the refractive index of NE, that means extraordinary wave, is now inside this circle. Why it is inside? Because like the previous case, the value of this portion from here to here is nothing but the value NE, and here from this point this value is NO. So, the lengthwise you can easily find that NE is less than NO. So, the typical index figure or the typical surface or two dimensional index surface figure is something like this in negative crystal. So, in the positive crystal, the ellipse will be greater than the circle, because refractive index of NE is greater than NO, and in negative crystal the refractive index of NE is less than the refractive index of NO. So, that means the ellipse will be entirely inside, it will never cross the circle. So, this is the feature of negative crystal. Well, after having the knowledge of negative and positive crystal, which will be very important in the later classes, because this concept we will going to use in our phase matching case. So, let us try to understand index ellipsoid. So, this is the general form of the refractive index variation. So, one can derive very easily the general form of refractive index variation, because the material is a 3-dimensional material. So, that means if I launch the light can be any angle. So, this angle is not restricted to 2 pi, rather it will be restricted to entire, there will be a cone of angle. So, if I launch the electric field k vector in any angle means any value of azimuthal angle as well as this. So, in 3-dimensional if I want to find out, okay. So, in 3-dimensional the figure is something like that. So far I was restricted the k vector in this, but here I try to launch the k vector in some angle here and also some azimuthal angle here. So, this is, so if this is say phi, so I have another angle psi. So, in 3 dimension this is the k vector. If this is my z axis, this is my x axis, this will be my y axis, and this is the figure of general figure of launching a k vector, and this k vector is now in air, hanging in air, having any angle with some azimuthal component here. So, in that case what happened, I will have, instead of having a surface index surface, I will have an index ellipsoid. So, this is a treatment where we can have this equation. So, ellipsoid equation one can derive. So, let us try to find out how one can derive. So, I can write the energy density in this form for electric field. So, E dot d, half of E dot d. So, if I write half of E dot d, then I can expand this as half of E x dx plus E y dy plus E z dz. So, this is the form of the energy stored, the potential energy stored because of the electric field inside the system. This is just for electric field, the energy is electric field, I am not talking about the magnetic field, but anyway this is the form. So, now D and E is related to this. Now, if K bar bar is a matrix form, so I several time I use that. So, if this is diagonalized, then dx, Ex, dy, Ey and dz, Kz has a relationship like this. So, dy Ex is related to this, dy Ey is related to this expression, and dz Ez is related to this expression. So, now what we will going to do, I just replace this Ex, Ey and Ez in terms of D, and if I do, then we will have something like this, dx square divided by epsilon kx dy square. Just replace E. So, here Ex will be how much, dx divided by epsilon 0 kx. So, epsilon 0 kx is dx divided by epsilon 0 kx is Ex. So, we will replace this here. So, if we replace this, we will have dx square divided by epsilon 0 kx in the first term, second term dy square divided by epsilon 0 ky, and third term we have dz square divided by epsilon 0 kz. If we have these three terms, and then if I divide this Ey to entire equation divided by Ue, so left hand side I have 1 and right hand side I have this quantity, this entire quantity. So, now what happened in the next case, after having this expression we have already there actually. So, I have a expression something like this. So, now what we will do, we will rescale the thing, we will rescale. So, rescale means we will just try to find out what is the value of x, y and z in terms of whatever is given here. So, if I write x, my x is equal to dx divided by root over of 2 epsilon 0 ue, dy divided by this quantity and dz divided by this quantity with respect to, I mean if I write in terms of x, y and z, then after rescaling we can have an equation, the same equation now have this form. So, try to understand that we have an equation, and from that I can change the thing in terms of x, y, this is called rescaling. After doing the rescaling, I have an expression in terms of x, y, z. Assuming x, y, z is my coordinate system like dx, dy, dz, because dx, dy, dz is nothing but the x, y and z component of the d vector. So, if a d vector is like this, so I can divide this d vector into 3 different components along x, along y and along z, and these 3 different components dx, dy, dz is rescaled by root over of 2 epsilon 0 ue, and we call these segments as our x, y and z, that is all. So, that means I am rescaling to the component of dx, dy, dz along x, y, z to x, y and z by dividing that. So, after doing that I have an expression like this, we got this expression x square divided by kx, y square divided by ky plus z square divided by kz, and now if I write the same expression at x square divided by, because kx now can be expressed at nx square, ny square and nz square respectively, kx, y, kz, then I can have an equation which is basically the equation of an ellipsoid. So, this is an equation of ellipsoid. So, we know that in 3 dimension if I have these things, so this is the equation. So, this equation suggests that here we have a figure, and in this figure we try to understand and in 3 dimensional form of these things. So, when x and y is 0. So, that means x 0 and y 0. So, that means this point. So, this is the point where the curve is cutting at z axis. So, at this point where the curve is cutting at the z point, this value is our n z. From this equation also we can find that x is 0, y is 0. So, z square divided by n z square is equal to 1. So, that means z value, that means this amount is nothing but n z square. So, that means n z is the amount of refractive index along this direction when x and y is 0. In the similar way, if I remove z, that means at z equal to 0, y equal to 0, that means z equal to 0, y equal to 0 means this point. At this point it is cutting here to the x axis, and this value is essentially our nx, the refractive index nx. In the similar way, the refractive index of ny is the cutting point at this point. So, once they are cutting x, y and z point, then we will have the idea how the refractive index is distributed inside the system, inside in 3D how they are distributed. So, all the different points we have a different kind of refractive index here, here, in this point we have different refractive indexes. So, once we have different refractive indices, so we can find out that what is the angle. So, this is some sort of 3-dimensional ellipsoid, and all points, all individual points are the individual refractive index for that particular angle or that particular direction. So, for example, if my k direction is somewhere here, so I will have a this point over the ellipsoid, I will have the value of n, and that will be the value of refractive index along that direction. If my k is on x axis, then it is cutting at this point. So, over the surface I have nx point. So, that will be my refractive index along this direction. So, this is the concept of index ellipsoid. So, after having the concept of index ellipsoid, we will try to find out one other important thing, that is the group velocity and its direction. So far we are dealing with the direction of k, but now we will try to find out in which direction the s will propagate. We know already that the k and s, these two vector will not be parallel if the system is anisotropic. That is the thing we have already figured out. But here we find out that the group velocity is the the direction of the group velocity is same as the direction of s vector. So, this treatment is quite straightforward. So, we will going to use these two Maxwell's equations. So, this is the Maxwell's equation in different notation, in k notation. We know that this cross product, this curl thing can be represented as I of k cross. If I do for Maxwell's equation, so two Maxwell's equation here we are going to use, or we have used, is curl cross E is equal to del B del T with a negative sign. That was the equation we use, it becomes this, and another equation is curl cross H is equal to del D del T. This is another equation that we used here. So, this is the corresponding form. So, these two, when these two equations are used in terms of k and omega, then we have these two expressions, these and these, and then what happened, I will just rearrange these things, k dot E, I just make a dot product with respect to H and I will get this. For second equation, I will get the dot product with respect to E, and right hand side I will get this. So, k dot E cross H is something that we want to find out. So, E cross H is nothing but the vector of S. So, we know that the S vector is E cross H. This is my definition of the Poynting vector. So, k dot E cross H. So, we have this equation. So, we have this equation A dot B cross C. So, A dot B cross C, I can write B dot C cross A. If I do B dot C cross A, then we have this equation. So, this equation basically one equation. In the similar way, I have this equation in my hand, A dot B cross C. Again I will write it is B dot C cross A. If I write, it should be this form, and if I interchange H and E, it should be E cross H with a negative sign, and the right hand side accordingly I will get this. So, now if I add this equation, this and this term here, I will have 2 of E dot E cross H or 2 of K dot S. Once we have 2 dot E cross F, then in the right hand side I have something omega multiplied by D dot E plus B dot H. So, D dot E plus B dot H is nothing but the total energy stored into the system in using this magnetic thing. So, now what we will do, this is the total energy is half of these things. So, now omega, if I now write omega, so omega will be 2 K dot S divided by this D dot E plus B dot H, and these 2 I can write as a denominator by divided by 2. So, here, so that I can write as a total in terms of total energy U. So, it will be, so finally we will have an expression omega is equal to K dot S divided by U. Now, we know that the groove velocity is something, if I write a vector, because velocity is a vector sign, it should be K omega. So, d omega, normally in the one dimensional we write d omega dk is our groove velocity. This is the definition of the groove velocity, d omega dk. So, here we are doing the similar kind of things, but since it is a dot product, I need to write this operator form. So, the del omega is Vg is del omega. So, when we do this del omega, then we will find that in the right hand side this k will cancel out because of this operation, and eventually we will have S divided by U. So, that means the Vg, which should be a vector sign, this Vg is along S direction. Now, if I try to understand these things, we will find that if k is this direction in an isotropic system, the energy is flowing that is perpendicular to the surface. So, S is the energy that is flowing perpendicular to the surface of this index. That is a very important thing. So, it will be perpendicular to the surface. But k is not necessarily perpendicular to the surface. K is perpendicular for this system where we have uniform refractive index, that is true, but here for extraordinary case we do not have a refractive index uniform, the refractive index is changing. So, k is not perpendicular, but S will always remain perpendicular to this surface. However, at this point S and k both are in same direction, and also in this direction, in x direction also you will see that here if I make a perpendicular to the surface, here I make a perpendicular to the surface, both are parallel, that means k vector and S vector will be parallel. But any other direction here, for example, we will find that S and k are not in same direction. So, there is an angle between, if this angle is delta, this delta is nothing but the Markov angle that we have discussed earlier. But the important thing you need to know that the S vector will be always perpendicular to the index surface. That is a very important information that we have, and that is the direction of the groove velocity as well. Well, finally, today we will learn an important thing, that the linear response. So, polarization, so far we are dealing with polarization. So, polarization is nothing but P is equal to, so polarization is something which is proportional to electric field and defined like this. But in anisotropic system, we know that polarization can be represented in terms of this chi bar bar. Chi bar bar is something which is not a scalar quantity, rather it is a tensor quantity. So, we need to write the thing in component form that we have used earlier. So, P now write in component form, and the first component of the P, ith component of the P will be represented by the chi as Ij and then Ej. So, now the refractive index can be represented in terms of chi also, and it will be 1 plus chi 1. So, now if I write this Ij and all these different components, then obviously we will find the refractive index is also some kind of quantity which is not same for all the values of chi, because chi ij is a quantity which can change by I and j. So, there will be 9 components. So, different kind of refractive index one can have, and that is the characteristics of the anisotropic system. But here the linear response means, we will learn this in the next class. Linear response means, so just let me show you this figure. So, this is a system where we have a nucleus and it is surrounded by the electron cloud. So, this is a nucleus which is surrounded by a electron cloud, and what happened, I am launching an electric field here. So, when the electric field is here, what happened that we have some kind of shifting. So, there will be some kind of shifting of the entire electron cloud. So, because of this shifting, there is a change of the position of the center of the mass of the electron. So, the nucleus is sitting here, and the entire electron cloud, because of the application of the electric field, will shift from this point to this point. So, there is a shifting. So, if I write this, so nucleus is sitting here and the negative charge is somewhere here. So, if it is a positive charge, negative charge, there is a charge separation, and this charge separation is appearing because of the launching of the electric field. And we know, so this is the more convenient figure. So, there are many dipoles can be generated. We know that dipoles is generated because of this separation of charge, positive and negative. So, this separation of charge gives a tiny dipoles into the system. There is a series of tiny dipoles, and this dipole basically gives the concept of the polarization. We know that the polarization is dipole moment per unit volume. So, dipole moment is nothing but the charge multiplied by the distance. So, we have a distance here and we have amount of charge here. So, charge multiplied by the distance is our dipole moment. So, dipole moment per unit volume is the polarization, and this polarization is now proportional to E. At least from this equation we can see that polarization is now proportional to E. So, that is why it is called the linear response. So, that means I am launching an electric field to the material, and as a result the electron cloud is shifting. When the electron cloud is shifting, we find there is a change of the position of the center of mass of the electron, and when the position is changing of the center of mass of the electron, there is a dipole, tiny dipole will generate, and in the entire material we have some series of dipole that will be arranging under this electric field, and as a result we will have the polarization. But this polarization is a proportional. If I assume this is a proportional to electric field, then this is a linear relation. So far we say something about the linear relation. In the future class and the next class also we will learn more about how this response is there, what is the meaning of response, what is response theory, and all these things in detail. So, here I like to stop this class. So, today we will learn very important concept, what is index ellipsoid and how the S vector and k vector are not parallel to each other. There is a angle deviation, and this angle is called the Markov angle. We have already discussed this earlier, and also the response and the polarization. So, when we launch an electric field, the material will respond in terms of the polarization, and this polarization is proportional to the electric field so far, and this is the linear, we call this linear response. So, with this note, let me conclude the class. Thank you for your attention. See you in the next class, and we will learn more about polarization and response theory. Thank you.